Welcome to the Hardware Access Framework Overview segment of Bloomy's EFT Module for TestStand demo series. In this video, we will provide a demonstration of how the Hardware Access Framework component of the EFT Module for TestStand can greatly reduce sequence development time, decouple hardware and software development, simplify maintenance, and improve sequence readability. The Hardware Access Framework is a hardware and measurement abstraction framework for NI TestStand. The half links human-readable instrument, connection, and signal aliases to physical hardware configurations using unit-under-test specific channel configuration files. It then interfaces with the hardware configurations in NI TestStand using specialized step types based on signal information, like make connection, read numeric input, or set power output, rather than using instrument-specific configurations. The step types are implemented as configuration dialogues in TestStand rather than requiring direct code calls. This reduces the need for intimate hardware, driver software, and connection knowledge, and provides a standard interface that all test developers can use, regardless of platform-specific instrumentation. This video will walk through the process of creating the configuration file and developing tests using the TestStand custom step types. But first, let's take a look at an example of how it all fits together. In our example, we first look at a configuration file. A signal alias, 5-volt input voltage, is mapped to a signal type, analog input. We then define which instrument alias from our Instruments tab will make the analog input measurement, in this case, our DMM. An abstracted connection alias from our Connections tab is selected for switching the DMM to the desired test point. Then, based on the signal type and instrument selected, some instrument-specific configuration information is required. In this case, the NI-DMM measurement type, DC volts, resolution, 5.5 digits, and range, 100 volts. In TestStand, we then drop down a step type corresponding to the signal type that we specified in our configuration file, in this case, analog input. We then configure the step type to point to our alias name. When the sequence runs, the Hardware Access Framework analog input step type will consult the configuration file for the specified alias and call the appropriate hardware driver with the correct settings to take the measurement. If instrumentation changes need to be made, such as changing the configuration settings or even the instrument itself, they can be made in the configuration file without affecting the test sequence. In other words, just like when developing automated test hardware, where typically the base system instrumentation is generic, and the test fixture maps that generic instrumentation to the UUT-specific connections and circuitry, when developing test sequences using the Hardware Access Framework, instrument drivers are generic, and the hardware configuration file maps the generic drivers to the test step configurations specific to the unit under test. The remainder of this video will walk through the steps to create our example measurement, including setting up our hardware using NI Max, creating our channel configuration file using the Hardware Access Framework Manager, and developing our TestStand sequence using the custom step types. Note that as with the majority of test sequence development using the Hardware Access Framework, no custom coding will be required. To start, let's first review where each of the major components gets installed. The Hardware Access Framework Manager, used for generating the channel configuration files, has a shortcut on the desktop and is also available from the Start menu programs in the Bloomy folder under EFT Module for TestStand 2016. The TestStand custom step types are available in the TestStand insertion palette under the Hardware Access Framework folder. A shipping example is available in My Documents under UUT Test Files and Tests. This shipping example provides an example of how to use the Hardware Access Framework when configuring a TestStand sequence, and also provides an example Hardware Access Framework channel configuration file. Finally, the drivers that are used by the Hardware Access Framework are in the TestStand public folder under Components, Step Types, Half, Plugin Drivers. And each plugin driver is installed as a LabVIEW packed project library with the source code included as a zip file. As part of our development, it's helpful if we first have some instrumentation. So let's create some simulated instruments in NI Measurement and Automation Explorer, or NI Max. While it's not required to have instrumentation installed, it makes the process of developing the channel configuration file easier. For this demo, I'm going to use the shipping example that ships with the EFT module for TestStand. It is in the TED example folder in the support files folder, and it's called tedconfigdata.nce. If we open up this file, it will allow us to import some simulated devices, including a PXI 4110 power supply, NI switch matrix PXI 2530B, a PXI 4071 DMM, a 6221 data acquisition card, and a 6515 industrial DIO card. All of these are very common instruments found in automated test equipment. When I click import, it will load these into NI Max, and we will now see our simulated instrumentation in our devices and interfaces folder. Now that we have our hardware configured, I'm going to create a new project in our UUT test files folder. So I'll navigate to My Documents, UUT Test Files, Tests, and create a new folder here called Half Demo. Inside this folder, we'll place our test sequences and our channel configuration files. So now I will open up our Hardware Access Framework Manager and save our new file to our test location, Half Demo, and I'll name it Half Demo Configuration. From here, I can now see that I have different tabs for instruments, signals, connections, and I also have two additional tabs for communications devices and messages, which we'll cover later in a different video. The purpose of each tab is to link human-readable aliases in the form of a name and a group to hardware configurations for each particular abstraction type. In general, each test sequence or ITA would have its own unique configuration file. The Instruments tab defines the physical devices in the system. Each physical device that is required for a particular test must have an entry in the configuration file with a unique alias, which maps it to the desired hardware access framework driver, physical address such as COM port, GPIB address, or MAX alias, and provide any instrument-specific configuration parameters. This alias can be referenced by the different connections and signals in the system in order to execute commands on the device. In TestStand, other than initializing and closing the device, TestStand does not directly interface with any instruments. The Connections tab defines the switching routes in the system. These could be matrices, multiplexers, general-purpose switches, digital output controlled relays, or any combination of these. Each connection route has its own unique alias on the page, which maps it to one or many physical connections potentially across multiple devices, each referenced by the instrument alias on the Instruments tab. Test developers in TestStand interface with connections by using the connection step type. They can then configure the connection to point to the desired alias within the step type configuration dialog. The Signals tab of the Hardware Access Framework Manager defines the stimulus and measurement I/O of the test sequence. Like everything in the Hardware Access Framework, each signal is referenced by its own unique alias. There are many types of signals, including analog I/O, waveform I/O, digital I/O, counters, power supplies, each with its own corresponding step type in TestStand. Like connections, signals interface with devices via instrument aliases. Signals may also call connections, which can be performed before their main operation and disconnected after. This is typical of multiplexed instrumentation like a switched DMM. The configuration file entry for a signal defines its alias, signal type, any connection information, and any instrument-specific configurations which are based off of the signal type. Test developers in TestStand interface with signals using the appropriate step type for the signal type defined. Just like when developing my ATE hardware, the first thing I like to do is to define my instrumentation. To do so, I navigate to the Instruments tab on the Hardware Access Framework Manager and start creating my aliases and mapping them to hardware. I'll start with my DMM, which I named DMM, and you'll note that an alias is really a combination of a unique name and group. For now, we'll leave the group blank, but we'll discuss them in more detail when we talk about signals. I then define the driver that I would like to use, and in this case it is NIDMM. You'll note that when selecting a driver, NI devices typically use the driver name corresponding to the LabVIEW drivers that you would typically develop with. Other instrument drivers are typically named for the instrument or family that they control and can be downloaded from the EFT support page by clicking on the button here. Now, once I've selected my driver, I can define the instrument-specific parameters, and in this case, all I have to define is the DMM resource or address. Here I select the DMM that we installed when we initialized our Measurement and Automation Explorer, the DMM 4071. I can save my file and now add some more devices. The next device I'll add is our switch matrix. I'll give it the alias switch matrix, and I'll select the driver, in this case, NI switch. Now when I select NI switch, I get different parameters that need to be set up for this particular driver. In this case, the switch resource name, which I'll point to the switch 2530 that we installed earlier, and I'll point it to the correct switch topology, in this case 4x32 switch matrix. Save our file and continue on. I'll add our data acquisition card and give it the alias DAC, point it to the correct DAC MX driver, and select the device that we installed earlier, our PXI 6221. I'll do the same thing for our industrial DIO. Also point it to the DAC MX driver, which are used to control it, and point it to our new device, the industrial DIO. Finally, I'll add our PXI power supply, which I'll give the alias power supply. In this case, it uses the NI DC power drivers, which has its own instrument setup. I'll point it to the correct max alias and set the initialization parameters, 20 volts maximum and 1 amp maximum. The next thing I'll do is create a test sequence file that links to our hardware access framework configuration file. To do so, I'll start with a blank sequence and drop in the initialize hardware access framework step type. This allows me to specify the configuration path in one of two ways. I could either specify the path directly or use the recommended approach of auto-detecting the path based off of the sequence file location. In order to do this, I need to save my sequence file at a place relative to the configuration file. So if I choose Save As and point it to the same location that we saved our configuration file, give it a name, half demo sequence, and save it. When I specify the configuration file now, I can now see that it's auto-detecting that configuration file we just created. I can then drop in the close hardware access framework at the end, and I've now implemented the two functions that are available to directly interface with instruments, initialize and close. With the instruments defined, I can now create my signal aliases. To do so, I'll navigate to the signals page and create my aliases and map them to the physical hardware, including which instruments I would like to use. In keeping with our demo, I'll create our 5 volt input voltage DMM measurement. I'll give it the name 5V input voltage. Choose my signal type, in this case analog input, which really just means there's numeric data coming into the system. This could be voltages or temperatures or currents. It doesn't really matter. It's just scalar numeric data. So I'll choose analog input, and I'll point it to an instrument, in this case, the DMM. And you'll notice this instrument alias is populated from the instrument aliases that we defined on the Instruments tab. So I choose my DMM, and when I do, I am prompted with some instrument-specific information. So I can choose the measurement type, in this case DC volts, the desired resolution, I'll go for 6.5 digits, and the range 100 volts. And you notice this populates the configuration file. Because I'm using my DMM, which is switched through the multiplexer, I need to define a connection route associated with this measurement. To do this, I'll navigate over to the Connections tab, create a new connection alias, which I'll call DMM25V input, and associate some physical connections with it. So I'll add one connection through our switch matrix, which is row 0 to column 0, and I'll add another one which also goes through the switch matrix, but is assigned to row 1, column 1. And you'll notice the drop-downs here are actually populated with the available connection names for this particular device. I can save this and go back to the Signals tab and point my connection to that connection route that I just defined, DMM to 5 volt input. I can now save my file and open up TestStand, where I can drag in the hardware access framework analog input step type. I'll give it a name, verify 5V input voltage. And when I click the configure button, it will launch the configuration dialog for the analog input step type. In this dialog, I can select our new alias 5V input voltage. I can also define what variable the measurement gets ported to. In this case, the default is step.result.numeric, which is used for numeric limit tests. But I may also select from the dropdown any other available numeric variable in TestStand. I can also select whether or not to leave my connection connected after the measurement is performed. By default, we leave this checked so that the connection is made before the measurement is taken, and then the connection is disconnected at the end. When I hit OK, changes are committed back to the TestStand sequence so that the measurement is performed when the sequence executes. I can then set my limits to between 4 and 6 volts so that when the test executes, it will result in a pass or fail value to the overall sequence. I'll now return to the Hardware Access Framework Manager and configure a few more signals. The first signal I'll configure is our 5-volt input resistance measurement. Using the same connection information and instruments as our 5-volt input voltage, the resistance measurement is often useful for safe to turn on tests. To do this, instead of creating a new signal type, I'm going to duplicate our existing row and just change our alias to 5V input resistance. I'll use the same signal type analog input and same instrument DMM and the same connection DMM to 5-volt input. However, I'm going to change the instrument specific configuration from DC volts to 2-wire resistance, from 6.5 digits to 5.5 digits, and from 100 volts to 100K ohm range. As part of this, I'll also update my units. Instead of volts, this measurement is done in ohms, and I'll make sure that my previous measurement, 5-volt input voltage, is in volts DC. These units will show up in the TestStand reports. Our example board has several analog amplifiers on it. So in order to test these, I'll first create our stimulus signals. Amplifier 1 stimulus will be an analog output using our data acquisition card. When I choose our DAC card, you'll notice that we have some instrument-specific configurations that are specific to the DAC card in analog output mode. So I'll choose our analog output 0, set it between -10 in a 10-volt range in the default terminal configuration. I'll then add a second channel by duplicating this row, call it amplifier 2 stimulus, and instead of analog output 0, I'll use analog output 1. I can now save this and create our response channels. So to do this, I'll call a new alias amplifier 1 measurement. This will again be an analog input, except this time using our DAC card. And now we see some DAC specific analog input configuration information. So I'll choose analog input 0, -10 to 10 volts. And in this case, it's going to be a differential input. I'll duplicate this row and point it to analog input 1. I can now save this and return to TestStand to implement these steps. So first I'll drop in my analog output, say set amplifier 1 stimulus, configure our analog output, and when I click on the configure, it will bring up our dialog box that allows me to select the stimulus that I'd like to use, in this case amplifier 1, and set the output value. And I will set this output value to 1 volt. Just like with analog inputs, we can also specify whether or not to disconnect any connections after our task is performed. However, in the case of output signals, you typically want to leave your output stimulus connected to your unit under test. Therefore, when setting output signals, you'll typically want to uncheck this box until it's time in your sequence to disable the output as a separate step. In this particular situation, it actually doesn't matter because there's no connections associated with this particular signal. I can now drag in my analog input measurement, say verify amplifier 1 output, configure our analog input, and now I see all of my different analog inputs, and I'll choose our amplifier 1 measurement. I can hit OK, and I will check that our measurement is between 7 and 9 volts. Now, as we look through the aliases in our analog input configuration dialog, you'll notice that we can see all of the different analog inputs defined by the system. Right now we only have 4, but if this grows to 1 or 200 different analog input measurements, it would be very cumbersome to find the alias that you are looking for. This is where groups can become helpful. If I return to the Hardware Access Framework Manager, I can see that every instrument, signal, and connection has a group column. And this group column can be used to more easily filter for the alias that you are looking for. So in this example, I have groups for power and groups for our amplifier. So I will define these as part of my configuration file. For the power signals, I'll give it the group power. And for the amplifiers, I'll give it the group amp. And I can edit this in either location, and it will automatically update. Now when I return to TestStand after saving the file, I am now able to update my steps to look for the appropriate alias using the group name. So my power input 1, I'll see I can use my power 5-volt input voltage. And on my amplifiers, I can choose the amplifier measurement. And I can either do that by directly specifying it or by specifying the name and group individually using separate drop-down boxes. And when I do it this way, I can actually filter by clicking the lock button for just aliases in a particular group or with a particular name. So if I switch this over to the power group, I'll now only see power measurements, where if I switch it to the amplifier group, I'll only see amplifier measurements. And this makes it a lot easier to filter for the exact measurement that you're looking for. Groups are also useful for batch or parallel process model operations, where you can define the alias signal name and the group can be correlated to the socket ID. This basic process of defining abstracted aliases, which map to hardware configuration information in a configuration file, then calling those abstracted aliases from TestStand step types, make up the basis of the Hardware Access Framework. From here, let's explore a few more of the step and signal types available. Each of the different step types in TestStand are broken down into sections based off of the I/O they perform. The Connections section directly interfaces with the Connections tab in the configuration file. This allows you to manually control the enabled or disabled state of a particular connection based off of its alias. I can also drop in signal types for digital input, digital output, analog I/O, counter I/O, waveform I/O, and power supplies. Each of these different step types has its own configuration file with the pertinent information for its signal type. For instance, the digital output allows me to specify the on or off state of a digital output configured alias. If I go to the Hardware Access Framework Manager, I can create a digital output step type. We'll call it test.do. Choose the digital output signal type, point it to our data acquisition card, and you'll notice that we now have digital output information that is specific to the data acquisition card. I'll choose port 0 line 3 and save the file. When I return to TestStand, I can now click on our digital output step type and select our new alias, test.do. I can make sure it's on or off as desired by the test sequence and hit OK. Some signal types, like waveform input and output, are much more complex. When I configure the waveform output step type, I can define a waveform that is output in a continuous or finite mode. Continuous will start the waveform executing and will allow it to run until the continuous stop function is called. So I can define what the waveform looks like, and I can actually display this waveform on a graph. So if I choose a 10 Hz waveform with a sample rate of 1,000 samples per second, and I display 200 samples with an amplitude of 1, I can now see my waveform that is going to be output. Now this could go out to a function generator or an NI DAC card based off of this signal alias. I can also take a waveform input measurement by dropping down the waveform input step type, configuring it, pointing it to an alias that is yet to be defined in the configuration file, and selecting the mode. Modes include configure and acquire, which is the default, configure only, which is often used to arm a trigger, or acquire only, which is used to fetch the data after the trigger has been activated. When I define my waveform input step type, I can define if I want to analyze the waveforms and output the frequency, amplitude, DC and RMS values, pulse width, and duty cycles. These go to the step.result.analysis variable. And I can also customize where these go by choosing the appropriate item, say frequency of the waveform 0, and outputting it to a particular TestStand variable, including local or file globals. Let's now take a look at the power supply output and readback functions. Whether you're talking to an NI-DC power supply or a third-party boxed instrument, the configuration in TestStand is the same. The specific details are stored in the configuration file. So I'll create a new signal called power output, and I'll link it to the power supply output step type. I'll choose our power supply that we configured on our Instruments tab and select which channel I would like to use. This is specific to the NI-DC power supply driver. I'll choose channel 0, and then I'll duplicate this and call it power readback. And instead of the DC power supply output, I'll choose the readback signal type. Same power supply, same channels. I can save the file and return to TestStand to configure my step types. When I configure the power supply output, just like every other step type, I can define the alias, power output that we just defined, and then I can set my voltage, current, and enabled states as desired. When I configure the power supply readback, I choose my readback alias, then define where the values are stored to. By default, they're stored to the step.result.voltage, current, enabled state, and status variables, but I can also copy them to any available TestStand variable, such as locals and file globals. Once you've implemented a few steps in the hardware access framework, you'll see that the process is as easy as creating an alias in the configuration file that maps to hardware-specific data, referencing that alias from the TestStand step types, and then repeating to create your own test sequence. For more assistance, you can review the Hardware Access Framework user manual, which installs with the EFT module for TestStand. It's available in the Bloomy folder under Documentation. This provides a step-by-step guide into how to develop tests using the Hardware Access Framework, including developing your channel configuration file, implementing the steps in TestStand, and provides detailed overviews of each of the different step types. It also provides instructions on how to create new drivers for the Hardware Access Framework. You may also review the shipping example that installs with the EFT module for TestStand. It's available at My Documents, UUT Test Files, Tests, TED Example, and includes an example test sequence and corresponding Hardware Access Framework configuration file. The test sequence includes examples of common tests performed by automated test equipment, including safe to turn on and power up tests. All of these tests are implemented using the Hardware Access Framework. So you'll be able to see common uses of the HAF in real-world scenarios, from simple tasks like setting power supply outputs and taking measurements, to more complex tasks like asynchronous waveform generation and acquisition. The corresponding Hardware Access Framework configuration file is set up to use the NI-Max configuration that we installed at the beginning of this video. It provides more in-depth examples on how to configure each of the instruments, signals, and connections in the system, and is a great reference for Hardware Access Framework best practices. For more videos on the EFT module for TestStand, including advanced topics with the Hardware Access Framework and overviews of the manufacturing operator interface and database reporting plugin, visit bloomy.com.